matrices. All right, what's a matrix? A matrix is this table of numbers. You can write any number, 2, -3, 11, 5, 7, 6 here. And first you have to know some words. These are called rows. It's a row. Whereas this is a column. So this matrix has 2 rows and 3 columns, and therefore we call it as a 2 by 3 matrix. I grew up in Korea, so I learned these in Korean. And in Korean, matrices are just called row column. That's what it's called, 행렬. So when we call matrices, oh, it's something that's made of rows and columns. And it's kind of nice because you always remember that row comes first and then the column. All right, adding matrices or multiplying numbers to matrices are exactly like vectors. You can multiply something to a matrix, say if you have 1, 5, 2, 3, then multiplying by 3 gives you 3, 15, 6, 9. There's not much going on here. And when you add or subtract matrices, you can only do it for matrices of same dimension. You're not allowed to add or subtract between matrices of different dimensions. So suppose I had 1, 0, 1, 2, 2, 0, plus -3, -3, 2, 1, 0, 5. You just simply add the corresponding elements. That's matrix addition. -2, -3, 3, 3, 2, just like that. There are no surprises here. Now, what gets interesting is when we define multiplication of matrices, and it goes like this. You can multiply, say, two 2 by 2 matrices in the following way. If you have 1, 3, 1, let's just say 4, 2, and you multiply -1, 2, -1, 3. Let's say we multiply. Multiplication is defined in a strange way. And there's a reason for it, which I can't really explain why at this point, because to explain the matrix multiplication, I need to talk about transformations using matrices, and it's a lot to say. Okay, so I'm just going to tell you how to multiply. The multiplication goes like this. You go across and down. So you just have to remember that. Across, down. Maybe you should follow me. Across, down. Across, down. That's how you multiply. Across, down. All right, what do I mean by that? You go across, picking up a row, and you go down, picking up a column. And when you pick a row and a column, what you're supposed to do is you're trying to do a dot product between the two matrices. So we're doing 1 times -1. Remember, dot product is component-wise multiplication, and then you add them up, right? So the first elements get multiplied together, second elements get multiplied together. If you add a third, then the third one will also be multiplied together. And after doing all the multiplication, you're going to add. So 1 times -1 is -1, 3 times -1 is -3, Negative 1 plus negative 3 is negative 4. And because it's the first row and first column, you place it in the first row and first column. Okay. Now let's take the first row and second column. It's 1 times 2, 3 times 3. So it's 9 plus 2, which is 11. Right? And that's first row, second column. Therefore, you put it in the first row and the second column. So there's 11 right here. And then second row, first column. 4 times negative 1, 2 times negative 1. So it's negative 6. Second row, second column. 4 times 2. 2 times 3. So that's 14. That's the result. Now, after defining matrices this way, you will realize that in order for matrices to be defined, you need the number of elements in a row to be same as the number of elements in the column. So, in general, if you have an n by m matrix, and you wanted to multiply this to another matrix, see, this is the number of rows, and this is the number of columns. So each row will have this many elements, right? So there are m elements in one row, and therefore there should also be m elements in the column. So you need this number, the very first number. The number of rows should match with the number of columns here. And these two numbers, they don't have to match. So let's say this is L. If you multiply two such matrices, you end up with an n by L matrix.
What happens to that?
That's the answer. You just.
Oh.
I mean, when do you get to use it? That's another matter. I'll tell you when we actually get to use this. Right now, this is just definitions and definitions without really telling you the purpose for doing these things. Okay. All right. Now, let me talk about. Yeah. So maybe I should give you an example that's like this. So if you had 1, 1, 2, 3, 2, negative 1. This is a 2 by 3 matrix, right? So what do we know about the second matrix if we want to multiply?
It could be a 3 by something.
3 by something matrix, right? So I need some 3 by something matrix. I'll just do a 3 by 1 matrix, okay? So I'll put a 2, negative 5, 1. Something there. And then if you multiply these across down, 1 times 2, 1 times negative 5, 2 times 1. So negative 1 is the first column, first row, first column element. And multiply this with that. 3 times 2 is 6, negative 10, so negative 4, negative 5. So you get that. Okay. So as you can see, this is a 2 by 3 matrix, and that's a 3 by 1 matrix, and the result is a 2 by 1 matrix. Okay? All right. Now there is a matrix where the result is the same after multiplication, and such a thing is called an identity matrix. So let me show you. So suppose you have 1, 2, 5, 8. And if I multiply this with 1, 0, 0, 1, the result is same as before. So let's see. Across down, 1 times 1, 2 times 0, so it's just 1. Across down, 1 times 0, 2 times 1, so it's just 2. Across down, 5 times 1, 8 times 0, so it's just 5. cross down, 5 times 0, 8 times 1, so it's 8. See? This was what we started with. Multiplying this, didn't do anything. Okay. So what do you call such an element? If the result, if the multiplication doesn't change anything, this element is called identity. Yeah. So this is called a multiplicative identity. Now, this is a 2 by 2 multiplicative identity. So in letters, people use I for the matrix. So whenever you see I, you would know that it's referring to this matrix. Okay. However, this is not the only matrix that would do it. In the 2 by 2 case, you would have, this will be the only one, but if you have a 3 by 3, multiplication of 3 by 3 matrices, so I'm tired of just putting numbers here, I'll just be very generic. So A, B, C, D, E, F, G, H, I. If you have this matrix times 1, 1, 1, and 0 everywhere, and if you do the calculation, you'll see that the answer is still A, B, C, D, E, F, G, H, I. And therefore, this one is the identity in the case of a 3 by 3 matrix. You call it I subscript 3. But and you can also think about I4, I5. All these matrices are the matrix where you have 1 on this diagonal and zeros everywhere. By the way, because of the way multiplication is defined, it later turns out that this diagonal of a square matrix is much more important than the opposite diagonal. So when you talk about a diagonal of a matrix, this is always what it means. This is called a diagonal of a matrix. And this one, the opposite one, people sometimes call it anti-diagonal. Okay. So whenever you talk about the diagonal of a matrix, it always means this one that goes this way. It's not that. All right, now let's talk about inverses. Inverse of okay, suppose I'm given A, B, C, D, a 2 by 2 matrix, and I want the inverse of this matrix. What does that mean? What does it mean that this is an inverse? What property does it satisfy?
1 over it.
Yeah, but what does it mean to be 1 over? Yes?
You can like flip it.
Okay, so you learned matrices somewhere, but in any kind of algebraic system, when you say it's an inverse of some other element, what does that mean? No, it really means the following. It's something that would multiply, or if any kind of operation is defined among the elements, and also you have something called an identity, then you say an element is an inverse of another element if, when you perform the operation, you recover the identity. That's what's called an inverse. Okay? So such an element is called the inverse, and we represent it as -1 over it. But this doesn't mean it's the reciprocal. It doesn't mean it's the reciprocal. Okay? This is just a way to write down the inverse matrix of this element. Okay? Actually finding out what this is a completely different matter. Okay? And you will later find out that it's not always true that whenever you're given a matrix, you can find the inverse of it. Okay? All right, and let's actually try to figure out what that is. We'll just denote this. This will be another 2 by 2 matrix. I know it's a 2 by 2 matrix because this is a 2 by 2. That's a 2 by 2. The only way you can multiply to 2 by 2 matrix and get another 2 by 2 matrix is when this object here is a 2 by 2 matrix, because we know the dimension, right? So I know that this must be some 2 by 2 matrix, x, y, z, omega. And to really figure out what x, y, z, omega are, we will substitute this thing here by the right one, and we will try to solve it. 1, 0, 0, 1. Okay, so we'll try to solve it. This times this, which is ax plus bz, is equal to 1. Has to equal to this one. Okay? This times this, which is ay plus b omega, should be 0. And cx plus dz should be 1. And then cy plus d omega should be 0. So we have a system of equations, and our goal is this. We want to figure out what x, y, z, w, z, omega are when you're provided by a, b, c, d. So in this system, you should, yes?
Should the cy and d omega be 1?
Oh, thank you. No, cy times d omega should, yeah, so this is 1 and that's 0. Thank you. All right, so so we're thinking of x, y, z, w, z, omega as the unknown and a, b, c, d as given. So you have 4 unknowns, and you're trying to find these 4 unknowns when you're provided by 4 equations, which means you can solve it, right? If you're given 4 equations for 4 unknowns, you can solve it. Okay? How do you solve it? You solve for one variable and start plugging into another one, right? So we can just blindly solve something that looks simple and plug into the next one and see if you can do it. Okay? Now, what's more interesting is you see that these 2 are the equations that have y and w. So it's really not complicated to solve. You just want to take these 2 as a system of 2 unknowns with 2 equations, and you can solve this, right? So let's first solve this by omega, so which is b omega is equal to negative ay, so that omega is equal to negative a over by. And I'm going to replace this over here, and let's see, that's cy plus d times, the omega is now replaced by negative a over by, and that's equal to 1. And now, since they both have y's in there, I can combine them, right? So here's what we do. This one is minus a dy over b. And because the second one has b in the denominator, let's multiply b and divide by b so that they have common denominator. So bcy over b, and I'm adding them, and that has to equal to 1. And therefore, I will get let's multiply by b. So I get bcy minusady equals to b, and then y would, if I factor the y out, it would be bc minus ad equals to b, giving you y equals to b over bc minus ad. Okay. And then omega would be multiplying negative a over b times b over bc minus ad. So that bb cancels. And for some reason, I actually like ad minus bc better. So I'm going to multiply minus downstairs. And I'm going to write it as a over ad minus bc. And this one also, I like the ad minus bc better than bc minus ad. So I'm going to multiply negative top and bottom to make it negative b over ad minus bc. So we got omega and y in terms of a, b, c, e. That's good. Okay. How about x and z? Well, x and z, if you look at the form, it's almost like these two, except the role of 1 and 0 is reversed. So you can just do the same exact calculation, or if you believe me, it's gonna be like, let's see, y omega. So y would be like x, and y was attached to, so let's see, y has negative b there. Okay, so y has b, so x must have negative d. Okay, so you're gonna see that x is equal to negative d ad minus bc. I'm just skipping the steps because it's boring. Okay? It's not very fun. So let's just say we solved it. Okay? Then z would be a, b, c. C is missing, so c over ad minus bc. Okay? All right. So here is what we found. We found that a, b, c, d inverse is equal to, they all have ad minus bc under it, so it's x, y, z, w, right? And x is negative d over, oh, okay, I messed up. Yeah, so this should be positive, that's minus. Sorry, I skipped the step. If we actually honestly did the math, this would be what we get. Okay. So AD minus BC, and then this will be this y, so it's negative B over AD minus BC, and this will be A over AD minus BC, and this is C over, no, this is C, this is negative C, and this is A over AD minus BC. All right, so I skipped the step, but if you really insist, you can try to figure this out yourself, and this is what you get. And that means I can, since all the denominators are the same, that means I can pull it outside as this and write it as dA negative B negative C. And that is actually a pretty important result, so you should memorize that, okay? That's called the inverse of a matrix. So the formula is 1 over AD minus BC, D, A, negative B, negative C. That's what it is. Yes?
So, like on the test, if you ask us to find the inverse, will you actually give us numbers or variables like that?
So on the test, if you're asked to find the inverse, you would be using this formula with the given numbers.
Oh, okay.
So this was just the derivation. I didn't
Yeah.
want to just pull this out of the hat. to